Swayam Prabha. Digital India. Educated India.
Welcome to the DTH sponsored course on micromachining. Today we are going to discuss laser beam micromachining part 1, LBMM abbreviation. Acknowledgement: Professor N.J. Vasa from IIT Madras, Chennai. His chapter on laser micromachining techniques and their applications in the book on Introduction to Micromachining. Second, advanced machining processes. Third, Syed Nadeem Akhtar, PhD student of IIT Kanpur. Fourth, book by Benedict G.F. on non-traditional manufacturing processes. Organization of the talk: Introduction to laser, types of lasers and characteristics, theoretical analysis of LBM and LBMM, that is laser beam machining and laser beam micromachining, working principle of LBM and LBMM, and process characteristics, process parameters, applications and conclusions. Here N is missing. Introduction to laser. Sun rays and a lens burn a piece of paper. This is the fun game being played by many kids in India especially. What they do, they take a lens, concentrate the sun rays on a piece of paper and burn it and tell to their colleagues, "Oh, I have a magic. I am able to burn a piece of paper." Almost on the similar kind of concepts. You have a laser gun, laser beam coming out with the help of the lens. You are concentrating it and concentrating on metallic piece or non-metallic piece. The temperature is so high that it can melt and even it can vaporize those materials, and this is the hardest material can be machined by this particular process. Material removal taking place in this particular process is by melting and vaporization, and sometimes only vaporization. Production of lasers. Hypothesis of Einstein: it is possible to use light energy to stimulate electrons that would emit light of same characteristic. Consider as an atom is brought to high energy level E3, and then from E0 to E3 it is taken, as you can see here, this is say at E0 taken to E3 by outside energy source. That outside energy source could be light, heat, electricity, etc. This atom is allowed to decay back to ground level, ground state energy level. As you can see here, from here it is decaying back to ground energy level, that is E0, that is shown over here. As a result, a photon is released. This photon contacts other atom. This atom will also decay back and release a photon. Chain reaction continues and stimulated emission of photon takes place. And this sequence of triggering clone photons from stimulated atoms or molecules is known as stimulated emission, and energy source is usually so powerful that most of the atoms of lasing material are at higher energy level and release of photons keeps going on. Transition by absorption and spontaneous emission between two given levels of an atom takes place, that I have already explained, from E0 to say E3 and then decay back from E3 to E0. Feedback mechanism. One mirror here, two mirrors, one mirror is here, another is here. One of them is 100% reflecting, while another mirror is 95% reflecting. This is the lasing medium. These are the two mirrors, and this is the energy source. It may be electricity, heat, light, etc. And this is known as feedback mechanism. That is the feedback mechanism, captures and redirects a few coherent photons. We have seen how photons are released back into the active medium. This is the active medium over here. Feedback mechanism stimulates the emission of some more photons. Also, it permits a small percentage of coherent photons to exit as laser light. As I mentioned here, 95% mirror that exits the coherent photons, that is forming the laser light. A large number of photons are available to maintain amplification process through stimulated emission, and that's why it is known as light amplification by stimulated emission of radiation, and the short form of this is LASER, that is laser. You can see here a schematic diagram of the helium neon laser. Mirror is here, 100% reflecting. Another mirror is here, that is 95% reflecting. This is the discharge tube containing helium neon mixture over here, and this is the cathode. Here is the anode, and this is the power supply. So you will have the laser light coming out from this 95% reflecting mirror. This is the laser beam which is coming out of it. So this is the power, is time is more or less constant. Pulses are there, and if it is a continuous pulse, then it will be like this, and if it is pulsed laser, then it will be like this: pulse, no power, no pulse, no power, and so on. Active gain medium, pump source, optical resonator, cavity, output coupler. You can see there. Now this is the light, and here is the laser light. This works as the external source for stimulating the atoms. Classification: you can have continuous wave laser, constant power for more than 250 milliseconds, and pulse laser. So laser, properties of laser: monochromatic, that is single wavelength, directional, low divergence. This is very important property, and because of this it is used in many specific applications. Beam spreads very little, it is more or less a straight line. Intense high density of usable photons and coherent same phase relationship continue. Types of lasers and their characteristics. Types of lasers and their wavelengths. Let us see. You have solid state laser, Nd:YAG lasers, liquid lasers, dye lasers, gas lasers like excimer laser, helium neon laser. You can have semiconductor laser like diode laser. Wavelength, photon energy, absorptivity, feature resolution. You can see here AR, KR, XE are rare gases. They are used here. HCl and F2 are halogen gases. and neon buffer gas and helium inert gas. They are all shown over here, and you can see the structure. Now these are the wavelengths shown over here for different kinds of the medium used for producing the lasers. 10,600 nanometer for CO2 laser, 1064 nanometer for fundamental Nd:YAG lasers, 632 nm for red helium neon laser, continuous wave, and then frequency doubled Nd:YAG laser 532, and then you have here 532 and this is 1064, that's double frequency, and 351 XCF and 248 KRF like this, and then ARF and F2. So different laser mediums gives different frequency waves. Excimer lasers, they are very useful, and at many locations or in many applications they serve very good purpose. Characteristics of excimer laser: they are ideal for near field imaging, little or no heat affected zone, because this is the thermal source for removal of material, but in this particular case it is minimal heat affected zone. High resolution, approximately 1 nanometer feature possible, so you can create around 1 nanometer features with the help of this particular laser. Tight control of feature depth possible, and large beam cross section. But disadvantages are also associated with excimer laser: frequent and costly maintenance of these lasers. Gas has a high consumption, it is expensive, toxic and corrosive in nature. Components require routine cleaning and replacement in case of excimer laser. Optics degrade and require replacement. Changes in gas chemistry affect beam shape and quality, because laser beam is being used for the purpose of removal of the material. So changes in gas chemistry affect beam shape and quality. Optics need routine cleaning. Optics used in the laser system, excimer laser system, that need routine cleaning. You can see here gas laser, solid state laser. These are the medium excimer, CO2, Nd:YAG, wavelength are given here. We have seen already these descriptions. Now solid lasers cannot be used for heavy duty work, used for spot welding, drilling, etc., because you cannot get very high power from this solid laser, and especially Nd:YAG laser, UV Nd:YAG laser. For metrology, biomedical applications or materials processing, this is quite good. Gas lasers, helium neon laser, CO2 laser and so on, they are light pointer, cutting, joining, etc., and they are very good for the use as a pointer for cutting purposes, for joining purposes and so on. So I need not to explain, I hope all of you know it. This is the millisecond, 1 into 10 raised to power minus 3 second is the millisecond, and like femtosecond, 1 into 10 raised to power minus 15 is the femtosecond, and picosecond, 1 into 10 raised to power minus 12 second is 1 picosecond. Types of laser continues. Gases are recirculated and replenished. Folded, resonated or axial flow CO2 laser. This can give you as good as 1500 watts energy, that is 1.5 kilowatt, for very high power. Transverse flow gas transport laser. This is not very high, but you can make the changes or modifications in the system by having transverse flow, and you can get still higher power. Large amount of gas volume is required. Beam is reflected several times before it escapes as a laser beam through a partially reflecting mirror to get high power. Computer control of the laser beam machining system to take advantage of high speed processing scanning is required, then only it becomes automatic and you can get very high processing speed. Motion is given either to the workpiece or beam or both, so that you can create different kinds of the features on the workpiece. Conditions to build a working laser. Condition 1, the energy source providing initial stimulation should be powerful enough so that majority of the atoms or molecules attain high energy level. We have already seen this attaining high energy level with the figure E0 to E3 and then reverting back to E0. Condition 2, to produce a laser, it requires a feedback mechanism, and we have already seen feedback mechanism where you had two reflecting mirrors, one is fully reflecting, another is partially reflecting. Laser hazards and classification. Class 1, low power laser, low level of damaging radiation. Then you have class 2, laser power, low power lasers do not cause eye injury accidentally, but can produce retinal injury with continuous intra-beam beam. So one has to be very careful in using these layers and making safe use of these lasers. Class 3, AB, medium power lasers. A, visible laser is visible, no eye injury within blink, 0.25 seconds. Injury possible with binocular or optical devices or by continuous staring at the beam, and this is not required. One has to be very careful, especially in the case of kids or youngsters. One should not try to blink on these lasers, otherwise they may damage their eyes. Lasers viewed directly can cause eye injury, that is what I mean. Class 4 lasers, high power lasers, they need extra precautions and control measures. Advantages of short pulse laser beam. Machining of nearly any solid and soft materials is possible. Very high intensities of ultra short pulsed lasers enable absorption even in transparent material. Efficient and fast. Minimal thermal and mechanical damage of the substrate material or workpiece material. Structure sizes down to the lower sub-micrometer range is possible, that means nanometer. High quality machining, burr-free drilling and cutting is possible by the lasers. Ultra short pulse lasers are excellent and universal tools for direct ablative microstructuring of solid material. A material layer with a lower ablation threshold can be removed from a substrate material with a higher ablation threshold without damaging the substrate. Since the threshold depends on the number of applied laser pulses per area, overcoming an ablation threshold can also be controlled by the pulse overlap. So these are some of the advantages which permits you for controlling the performance of the ultra short pulse laser. Theoretical analysis of laser beam and laser beam micromachining. Laser beam with Gaussian energy distribution. This is the Gaussian energy distribution of energy. You can see here peak and then follows the Gaussian law. I current, x y function, I0 e raised to power minus x square plus y square whole divided by r square. P is the laser pulse or laser beam output power, and A energy absorptivity. Then peak intensity I0 is given by A into P divided by pi r square. Taking y is equal to 0, equation 1 becomes, this is the equation 1, becomes Ix is equal to I0 e raised to power minus x upon r whole square, this particular equation. So delta S has dimensions delta x into delta y in x and y axis respectively. Delta S is equal to delta x into delta y. The leisure power applied on area delta S is given by, this is the power delta P applied on area delta S into I0 into e raised to power minus x over r whole square. Note, width of cut remains constant and limited to diameter of the laser beam. Cutting path may be considered as a line along the center line which is subjected to the peak power where it cuts the deepest point. If the workpiece moves under the laser beam with a uniform speed v in millimeter per second, then time for the laser beam to pass the small area delta S is given by delta t is equal to delta x over y, because delta y is taken as 0 earlier, so it is moving in the x direction only, and delta x over v, that will be give you the time. Substituting for delta x from equation 6 into equation 4 already shown to you and substitute the result in equation 5, then the total energy absorbed by small area delta S given by E is the energy, delta P is the power, delta T is the time, I is integrated minus n to plus n, minus n to n, I0 substitute the value of delta P, delta S over V into delta Xi e raised to power minus x over r whole square. Laser beam with Gaussian energy distribution for a given material, weight of material W vaporized by the total absorbed energy E. Here it is assumed direct vaporization is taking place, definitely after melting vaporization will take place. So it is calculating that W is equal to energy required upon E upon Q. This will give you this is the unit mass or weight requires energy for vaporization is the total energy available, L raised to equal to L n to infinity minus n to plus n I0 e raised to power minus x over r whole square delta S over VQ delta Xi. We have already derived this equation earlier. Q is material specific energy of the material required, that is Q is equal to C into Tm minus Te plus Lv, where C is the specific heat of the workpiece material which is being machined, Tm is the melting temperature, Te is the ambient temperature where it is working, and Lv is the latent heat of vaporization. On the small area, the depth of cut is obtained from D is equal to W over delta Sp, where delta Sp is the specific heat and W is the total heat available. Laser beam with Gaussian energy distribution continues. Substituting for W and delta S from the equation given previously into equation 10, the depth of cut D is calculated as L limit n to infinity I0 e raised to power minus x over r whole square delta S over V delta Q VQ delta SP into delta Xi. So you can simplify this and you will get this particular equation. When n tends to infinity, that is here, delta S tends to 0 or delta X tends to 0. The above summation equation becomes an integration equation. D is equal to 1 over Q rho minus infinity to plus infinity 1 over V I0 e raised to power minus x over r whole square dx. And you can simplify, and to get this particular equation, 2I0 r over v cube rho 0 to infinity e raised to power minus x over r whole square dx over r. After integrating equation 12 and substituting with Gaussian energy distribution from equation 2 and considering the absorption, the depth of cut is given by this particular equation, where we have already derived the equations in the earlier. They can be simplified and written in this particular form. Here this is equal to this, and this will cancel by this, and you will have the under root pi only. Above equation reveals that the depth of cut is varied linearly with laser power. You can see the relationship. This is the depth of cut, and varied linearly with laser power, that is P. So it is a linear variation of D with P, and non-linearly with cutting speed, and it is varying non-linearly with cutting speed. Now here material removal rate is to be calculated. So let us see time taken by the laser beam to pass the small area delta S with a uniform speed v is given by delta t upon distance to be travelled by speed or velocity, that is given over here. That will give you the time. The total length of the workpiece to be L, then you can integrate it, sum up minus n2 plus n delta xi L equal to L, and so the total time taken by the laser beam to pass the whole workpiece is T is equal to L over V, where length of the workpiece is capital L and V is the speed with which it is travelling. Further, material removal rate is equal to L into 2R into D divided by L by V. So you get 2R dV, where D is the depth of cut and R is the laser beam radius. So putting the value of D from equation 18, you can get D is equal to A over Q R rho under root pi into P divided by V. So MRR becomes finally 2R into V into A over Q R rho under root pi P over V. That if you simplify, you get finally 2A P over Q into J over pi. Now rho over pi, sorry, this is rho over pi, that is over here. So this simple equation, from this simple equation you can calculate theoretically what is the material removal rate in case of excimer or rather than laser beam micromachining. Working principle of laser beam micromachining: energy input in the form of heat, electricity, light, etc. Output, energy output in the form of laser beam, useful for various activities like manufacturing, medical, etc. This is the folded laserinator axial flow carbon dioxide laser taken from the book by Benedict. You can see over here, this is the output mirror which is partially reflecting. This is a highly reflecting mirror which is having 100% reflectivity, and here are the anodes, these two, they are the anodes and these are the cathodes in the system made over there, and these are the cathodes over there. And you have the turning mirrors which are reflecting the laser beam, and here it is regulated power supply is over there. Electrodes are kept at both ends of the tube, as you can see over here. Electric current stimulates gas or other lasing medium, atoms, molecules in the tube. Feedback mechanism consists of a set of parallel mirrors at the ends of the tube, that here both are here on this side, otherwise it is at one end and second one is on the other end, where there are only single flow. One mirror fully reflective, another mirror, other one partially transparent, which gives laser beam as output. So laser light is monochromatic in nature, we have already seen it. Wavelength varies in a very narrow range of the spectrum. A simple lens focuses and concentrates laser light in a very small diameter and high intensity, called as a laser beam. Laser light is coherent, it travels in phase. This is very important characteristics of the laser light in nature, and low diverge. This is another very important property because it travels almost straight rather than bending etc. in this direction or diverging in any direction. Use of laser in material processing requires high power intensity laser. Machining operation requires 1.5 into 10 raised to power 6 to 1.5 into 10 raised to power 8 watts per centimeter square laser heat intensity, and workpiece is kept very near to the focal point of the laser. This is very important, that workpiece surface from where material is to be removed should be kept near the focal point. Just I would like to explain it here with this figure. Suppose this is the figure which is being machined, this is the workpiece which is being machined and laser beam is here. So this is fine, it is removing the material from here and focal point should be here only. But if you have already machined the workpiece and your laser beam should come over here, because this is the surface to be machined. So not here, this should have its focal point over here where the material is being removed from the workpiece surface. This is what it means, and this is very important characteristic requirement. So this is a schematic diagram. You have laser and you get the beam generation. Workpiece is here. You can travel the beam workpiece in x direction as well as y direction with the help of the motor, auxiliary, and workpiece positioning system is there. Some other line diagrams are given over here. Machine vision is there, target illuminators are there. Most of the things we have already seen. Focusing lens is there, workpiece is there. Precision motion stages you will have so that it can move precisely in x, y directions. Laser and working material interaction. Now please see it carefully. This is the laser beam. Heat conduction is taking place when laser beam is interacting with the workpiece. Laser beam surface melting taking place over here and heat is conducted inside the workpiece surface. Laser beam here surface vaporization is taking place, and you can see here these are the vapors. Vaporization vapors are coming up, molten material from there vapors are coming up. Plasma formation is taking place over here as you can see, and then laser beam vapors are going out and this is the molten pool and ablation is taking place. The light energy absorbed in the material is converted into heat and its conduction produces a temperature distribution in the material, that is workpiece material. Depending on the magnitude of the temperature, the material experiences heating, melting and vaporization. I have already mentioned to you that melting and vaporization is the main mechanism of removal of material, but in some cases it can directly vaporize the material. The laser removes the material through melting and vaporizing the material. The high pressure created during the melting and superheating of liquid after the end of the laser pulse eject the material at a high speed. Ejection of this molten material is essential so that you can create the feature. Sometimes if the material is not completely vaporized, particularly if it is expelled from the depth, then it cools quickly and forms what is known as recast layer, because if it is ejected out and it cools over here on the workpiece surface, then it will form what is known as recast layer, and this recast layer has to be removed before the part or the component can be put into assembly or it can be used. Assist gas and melt pool. High speed assist gas is carving out a kerf in molten material. What is kerf? We have already seen. You can see this picture. This is the laser beam. This is the molten material, molten metal entrapped into gas. These are the gases on the top. This is the melt depth, and then this is the cut depth is there. This one is the cut depth. Absorption and reflection of laser light. You can see here a schematic diagram of absorption and reflection of laser light in a solid. It is given Iz is equal to 1 minus R I0 exponent raised to power minus Az. A is equal to 4 pi k over lambda. I0 is irradiance of the incident laser beam. R is the reflectance of the solid surface. A is the absorption coefficient having a dimension of per meter into 1 upon A, represents how far the light propagates before complete absorption, known as optical penetration depth. That is what is shown over here, 1 upon A. The spot diameter D of a focused laser beam can be reduced to a few micrometer. Depending upon the focused laser beam diameter, you can create the features of respective dimensions. Depending on lens's focal length, laser wavelength, and the diameter of unfocused beam, D is equal to 4 lambda f over pi d. Now A NDR laser beam, lambda 1064 nanometer, we have already seen that is the wavelength, with initial diameter of 2 millimeter, is focused with a f is equal to 50 millimeter lens. The spot diameter will be about 34 micrometer. So that is how some calculations has been done, and you can get 34 micrometer spot diameter. Process characteristics and process parameters. Laser beam micromachining process parameters. Lens system with or without mask focusing, this is shown over here. Material to be machined, material properties, coating properties, temperature, continuous wave or pulsed laser, wavelength, energy, pulse width, frequency, beam characteristics, and medium, pressure, composition, application of nozzle, fluence, and interaction time. So the selection of wavelength with a minimum absorption depth ensures a high energy deposition in a small volume for rapid and complete ablation. The pulse duration influences maximum peak power and minimizes thermal conduction to the surrounding work material. The duration of the laser pulse is one of the most critical process parameters which significantly influences the precision and surface quality of the laser machine part, and precision of the machine part is very important feature. The next parameter is the pulse frequency. If it is too low, all of the energy which was not used for ablation will leave the ablation zone, allowing cooling, and that is not desirable. Then the efficiency is going to be low. Comparison of machining methods, that is just I will look at it. Excimer laser Practical resolution limit 5 micron, CO2 laser 200 micron, NdArc laser 50 micron, EDM 100 micron, chemical etching 250 micron, mechanical 100 micron, and so on. While attainable aspect ratio is depth of the machine feature to the, say if it is a hole, diameter of the drilled hole. 100:1, CO2 laser 100:1, NdArc 100:1, EDM quite comparatively small 20:1, and chemical etching 1:1.5, and mechanical 10:1. Taper, almost in all cases taper is obtained except mechanical one. Side effects: maximal laser recast layer, CO2 layer recast layer, burying thermal damage, recast layer, burying thermal damage in NdArc laser also. Surface finish is poor in case of EDM. Undercutting, definitely recast layer is there in EDM, and thermal damage is also there in EDM, which is not written here. Chemical etching, undercutting is there, but there is no thermal damage, no recast layer. In mechanical, burring is there, deformation is there, and wear is also there. So you can see each process has its own merits, and some limitations are also there with each process. So you have to choose the appropriate process, keeping in view economy, efficiency or material removal rate, and definitely the side effects to the equipment as well as to the operators. Laser micromachining versus other processes. Quickly, let us have a look at it. Criteria: material versatility. Laser micromachining, yes, you can machine conducting, non-conducting materials, you can machine magnetic, non-magnetic materials. Other micromachining techniques, no technique works with all materials, just like EDM works with electrically conducting materials, or magnetic abrasive finishing works mostly with non-magnetic materials. Initial investment is limited, it is high, clean room equipment in some processes is required. Material property requirement, not much constraint. Thermal conductivity and reflectivity should be low. This is very important point, because certain materials are there which cannot be machined by laser. So thermal conductivity is main and reflectivity, these two are main consideration while selecting the process as laser beam micromachining for the given material. Specific properties required in specific processes like electrical conductivity in EDM, ECM, crystal orientation, chemical reactivity in chemical machining, and so on. Heat affected zone very small in case of laser micromachining, large or larger in case of EDM. Depth control fine in case of laser beam, can be around 100 nanometer. It is coarse. Random spark generation in EDM also creates a problem. Resolution limited, greater than 500 nanometer. Fine possible electron beam can give around 100 nanometer. We have already discussed these processes, electron beam, EDM, etc. Complexity, one step pattern projection technique, scanning over whole area is slow. Energy, force, directionality is high, while in these processes, other advanced machining process, micromachining processes, it is low. Machining forces are almost no, because only thermal forces or thermal load is there, no mechanical forces are there. But in some cases here, mechanical forces are there, in some cases no mechanical forces are there, just like turning, milling, etc., or even in case of some advanced machining processes, some forces are acting over there. Materials parameter, and laser beam micromachining performance, reflectance, absorption coefficient, specific heat, thermal conductivity, thermal diffusivity, latent heat of melting, latent heat of vaporization, transformation temperature, melting temperature, vaporization temperature. These are the parameters which are going to control the efficiency of the laser beam micromachining. All of them have their own effect. You can see here laser is going on the workpiece surface, and you can see different phenomena that is taking place. Absorption, skin depth, penetration depth, absorption is taking place over here of this laser beam or light. Heat transportation, thermal conduction is taking place, as you can see in this particular conduction is taking place in this workpiece surface. And then you have the temperature rise all around, and heat affected zone is produced, that we have already seen, and dt raised to power half, heat, penetration depth, melting, etc. So you can see various phenomena taking place, and then evaporation of the material can take place depending upon the material characteristics, and surface cooling, ablation takes place. So this way we can see that material properties have significant effect on the performance of laser beam micromachining as well as laser beam macromachining. Process parameters, some of them we have already seen. If the residual heat can be retained by limiting the time for conduction by high frequency, the ablation will be more efficient. More of the incident energy will go towards ablation if frequency is high, and less will be lost to the surrounding work material due to conduction, etc., or convection to the environment. The beam quality also influences the uniformity in micromachining. I can tell you, when beam is there, how is the energy distributed within the beam? Is it like this, or is it like this, or is it like this? All of them are going to affect the performance of the process and characteristics of the machine surface. Effects of process parameters like this: wavelength, focal length of lens, they affect the feature size, ablation rate, optical absorption, reflection, transmission, resolution. Beam size, focal spot size, depth of focus, intensity. Beam energy, pulse width, they affect size of heat affected zone. Peak temperature is also affected by them. Pulse repetition range, depth of material removal, depth of focus, aspect ratio, vacuum or inert gas environment, amount of redeposition, size of recast layer. So you can see here different process parameters are affecting the characteristics of the machined component. Laser beam and depth of focus, let us see it. Say this is the beam dimension. After passing through the lens, this converges like here, and in this zone depth of focus delta f, this is very important to note. Whenever you are putting it on the workpiece, it should lie this part somewhere here. The surface which is to be machined should lie at this place, in this area. Then only you will get the best performance. If it is in this zone or if it is in this zone, you will not get correct or high performance of the process. And this is known as a focal length. This is the beam divergence. I told you in the beginning also that very small divergence is there, and this is exaggerated over here to show you and to appreciate you. And this is the minimum spot diameter. This is the minimum spot diameter. Now, spatial intensity distribution of laser beam, as I showed you in the earlier slide, that here also the intensity distribution, laser light intensity distribution is something like this. That means at the center it is the maximum, then it is distributing. So you can put it here in this particular zone and you can find the intensity distribution over here like this here, and then you have this kind of the beam like this. So somewhere here in the beam, at the center of the beam, you are going to get the maximum intensity, and on this side of the beam and here you are going to get comparatively lesser intensity. So beam parameters: wavelength, spatial mode structure, brightness, position, beam west, this is known as west, this part, polarization, spot size. This is the beam, you can see over here, focusing lens is there, beam is there, and this is focused on the workpiece over here, and nozzle is there. You can see some new feature over here, some sealing lens over, some kind of the gas is being added to the beam over here through this side zone, that you can see over here clearly. So this will come wherever laser is focusing on the workpiece surface, and it will definitely affect the machined surface characteristics. Gas assistance in laser beam machining. So you can have the assistance of the gas depending upon your requirement of the component. Now very interesting one, machining with long pulse lasers. You can see over here you can see over here, when long pulse lasers are being used, please see it carefully, this is very interesting one. You have the micro cracks over here that you can see, and you have the heat affected zone. Heat transfer is taking place in this particular direction, and change caused due to adjacent structure, and you can see the damage to the adjacent structure wherever it is taking place. And this is the recast layer, and you know, this is the melt zone or molten pool over there, and ejected molten material is like this. This will go out and may get deposited over here, and once it gets deposited over here, it forms a recast layer or debris over there. So when you are using long pulse laser, there are many disadvantages of using long pulse laser. So for a high accuracy, we always recommend machining with short pulse laser. These are the short pulse laser, and you can see all these problems here: recast layer, heat affected zone, debris over here, all of them are absent over here, and you get neat and clean cutting of the workpiece with short pulse lasers. You can see here pictorial view, this is the effect of laser pulse width, this is the kind of the one you are getting, this is the another one. So short pulse laser something like this, with long pulse lasers you can get something like this. What we have done in this lecture: introduction to laser, introduction to laser, production of lasers, characteristics of lasers, types of lasers and characteristics like gas laser, solid laser, liquid laser. This is liquid laser and semiconductor laser. Other way of classifying them is nanosecond laser, femtosecond laser, picosecond laser, excimer lasers, etc. So in different way you can classify them. Theoretical analysis of laser beam machining and laser beam micromachining. We have seen how to calculate the depth of penetration, how to calculate the material removal rate, and we have also seen the taper angle that you are going to get. Theoretical calculations for calculating intensity, material removal rate, depth of machining during LVM and LVMM. Working principle of laser beam and laser beam micromachining, how it removes material during LVM and LVMM, interaction between laser beam and work material, and some effects of type of laser on the machined workpiece characteristics. Thank you very much.